Welcome to this explainer. So, we've all seen those incredibly satisfying internet videos, right? The ones where massive machines effortlessly crush bowling balls, flatten soda cans, or just absolutely obliterate whatever is put underneath them. But today, we're going to look past that internet spectacle. We're diving deep into the invisible physics and the brilliant hidden engineering that makes molding solid steel look like child's play.
Okay, let's jump right into our blueprint for today. We'll be covering 1. The magic of hydraulic power. 2. Pascal's law and pressure. 3. Why we use hydraulic oil. 4. The myth of the pump. 5. Inside cylinders and pistons. And finally, number 6. Generating unstoppable force. Let's get into it.
All right, kicking things off with section 1, the magic of hydraulic power. To really get this, we have to rewind to the late 18th century when inventor Joseph Bramah first patented the hydraulic press. Now ask yourself, how does a relatively compact piece of machinery generate the thousands of tons of compressive force you need to, say, forge an airplane part or stamp out a car door? It's not magic, and honestly, there is no massive room full of complex mechanical gears doing the heavy lifting. The secret weapon here is actually liquid.
Which brings us perfectly to section 2, Pascal's law and pressure.
The real secret sauce behind this raw power is a 17th century scientific breakthrough called Pascal's principle. Because liquids are basically incompressible, they act as the absolute perfect medium to flawlessly transmit force from point A to point B. When you push on a fluid that's trapped inside a closed system, it doesn't just absorb your push. No, it immediately and perfectly pushes back against every single wall of its container with equal pressure. This is where pressure multiplication comes into play, and it's a real game changer, since pressure equals force divided by area. If you apply a tiny little force, say 20 newtons, to a small input called a master piston, that exact same pressure travels through the liquid to a much larger output, the slave piston. Because that slave piston has a way bigger surface area, the total force output is multiplied tremendously. In this case, shooting all the way up to 2,000 newtons. It's literally the exact same physics as tapping your car's brake pedal with your foot. A small little input from you effortlessly multiplies into a massive clamping force that stops a 2-ton speeding vehicle.
Moving right along to section 3, why we use hydraulic oil.
Let's talk about the fluid itself because its behavior is absolutely crucial. You might be thinking, well, why not just use water? It's cheap. And yeah, we do see water used in tiny DIY robotic arm toys, but for serious industrial machines, specialized hydraulic oil is an absolute must. Think about it. Water causes rapid rust, it freezes and boils way too easily, and its viscosity, its thickness, is incredibly thin at basically just 1 centistoke. Under the extreme heat and pressure of a factory press, water would literally just boil into steam. Hydraulic oil, though, it's specifically formulated to lubricate all the moving parts, prevent rust entirely, and handle intense thermal stress like a champ. The key takeaway here is viscosity. Hydraulic oil is engineered to sit right in this perfect sweet spot of 13 to 400 centistokes. Common industrial grades like 32, 46, and 68 give us a fluid that is thick enough to perfectly seal the microscopic gaps inside the machine, but still thin enough to be pumped super efficiently without wasting a ton of energy. Okay, time for a quick, counterintuitive fun fact. Remember just a minute ago when I said liquids are incompressible? Well, actually, scratch that. Under the totally extreme stress of a hydraulic press, the oil does actually squish just a tiny, tiny bit. At 140 bar of pressure, it compresses by about 1% of its volume. Now, in massive industrial systems, that 1% really adds up. It basically acts like a giant coiled spring, meaning engineers actually have to install special decompression valves to safely bleed off that trapped energy. Otherwise, the sudden release could completely blow out the fittings.
All right, section 4, the myth of the pump.
If you take absolutely nothing else away from this explainer today, make it this one surprising fact. A hydraulic pump does not create pressure. I know, crazy, right? Its one and only job is to create flow. If a pump just pushes oil into an open loop that dumps right back into the storage tank, the pressure gauge is going to read absolute zero. Zero. Pressure only builds up when that flowing oil hits an obstacle or a heavy load. And the plot definitely thickens when we look at the specific types of pumps these presses use. They use what are called positive displacement pumps, things like gear, vane, or piston pumps. With every single rotation of the motor, they aggressively force a fixed exact volume of oil into the system. They literally cannot stop flowing oil. So a mount in the machine's ram hits a thick piece of solid steel and stops moving. The pump keeps pushing oil, but the oil has nowhere to go. Resistance skyrockets immediately, causing a massive, dangerous pressure spike. This is exactly why every single hydraulic circuit absolutely requires a dedicated pressure relief valve to bleed that excess oil safely back to the tank. Without it, you're looking at a literal explosion of the machinery. Let's move on to section 5. Inside cylinders and pistons. This right here is the dynamic duo of the press, built out of incredibly robust, pressure-rated steel. First, you have the smaller plunger cylinder. This acts as the initiator. It uses its smaller diameter to push the hydraulic fluid deep into the system. That fluid travels through high-strength hoses until it slams into the much larger main cylinder, also known as the ram. Thanks to Pascal's law from earlier, the system trades distance for an absolutely unstoppable multiplication of force, driving the anvil downward.
And what's really amazing is the sheer variety of how these cylinders and pistons are housed. The architecture is incredibly versatile. You've got H-frames, which are shaped perfectly for super stable heavy industrial fabrication. C-frames have this open, single-arm design so an operator can easily get in there for fast, repetitive stamping. A 4-column press guarantees perfectly balanced force for complex, delicate shapes. Then you have horizontal presses, built specifically to apply sideways force to straighten massive, extra-long steel beams. There are even highly specialized wheel presses, designed purely to press gears and bearings onto gigantic locomotive axles. And finally, Section 6, generating unstoppable force. Let's put the whole puzzle together and watch this process flow from start to finish. First, clean oil is pulled from the reservoir. Next, our pump relentlessly pushes that fluid out into the circuit. Then, a directional control valve, usually a 4x3 solenoid valve, routes that oil perfectly to the top port of our cylinder. The ram extends downward, right up until it slams into the solid metal workpiece. Bam! Suddenly, the oil has nowhere to go. That physical resistance halts the flow, and within milliseconds, the pressure behind it violently builds up. That pressure multiplies across the wide surface of the piston head, generating so much force that solid steel simply yields and bends to the machine's will. Now, to put the engineering safety into perspective, look at the huge gap between the typical working pressure and the peak survival pressure. Engineers are incredibly smart. They purposely operate these presses at a much lower working pressure, say 100 bar. That is drastically lower than the pump's maximum rated pressure of 210 bar or its absolute red line, peak survival pressure of 250 bar. By leaving this massive safety buffer and setting that all-important pressure relief valve to open just 10% above the working pressure, the press can operate safely, quietly, and endlessly without tearing its own internal components to shreds. So I really hope this teardown shifts how you view fluid dynamics. Just take a look around your room right now. The next time you look at the perfectly stamped door of your car, or the clean edges of a microchip inside your phone, or even just the smooth ceramic tiles in your bathroom, I want you to remember this. Take a second to wonder just how much of our modern, precision-shaped world is entirely reliant on the quiet, totally unstoppable force of trapped liquid. Thanks so much for joining me on this explainer, and definitely keep questioning how the world around you is built.